This is what you guys should be getting for the critical numbers. Here's the showing that it is that derivative. It's a product rule, right, with a chain rule in there. So that's how that becomes that derivative. You factor it one more step there. You can see the critical numbers. They each have multiplicity 1, so it's going to change signs everywhere. Why does this guy not give me any critical numbers? That factor. Exactly. It's asymptotic at 0, so it can't be 0. I like that. You can't raise something to a power and make it 0. I like it. You make it as tiny as you want, just not 0. So that's why I only get 2 critical numbers. Now this whole thing, this whole part C that we do, this step here, this is called the first derivative test because we're testing the critical points using the first derivative. There will be a second derivative test which will be quicker if the second derivative is easy to get. So it really is sort of a, the second derivative is disgusting. I'm like, no, screw that. Let me just make a sign here. If the second derivative is easy as shit, I'm going to do that because it's a lot quicker. We'll see that when we get to what the hell the second derivative means. So here for the sign diagram, negative 1/2, 0, 0. It's multiplicity 1, so it's going to be changing signs everywhere. So if I just plug a 0 in, that's 1 times 1 times 1. It's positive. And so it's going to have to be negative out there because it's got to change the signs across its roots. Or if you don't like multiplicity and you enjoy doing extra work, you can plug points in from each region. Increasing, decreasing should be a very simple question now. Increasing where? Negative 1/2 to 1/2. So it's decreasing everywhere else. And then what's the min? Yeah, a negative 1/2, it's a min's going down and coming up. So there's a min at negative 1/2, and when you plug negative 1/2 into the function, symbolically I get negative e to the negative 1/2 divided by 2, and then, you know, whatever the hell that is if you want to put it in a calculator. We will be getting to the point where we're graphing this by hand, so you will want to give a good decimal estimate, so you can just find it. Yes? No. So, where am I plugging negative 1/2 to figure out the point? The function. I don't care about it. I know the slope is 0 there. I know it is, because it's a critical number. I want to know where the point is. So we can do that before we ever did any calculus, because they just plug it in the function to see where the point is, right? Again, that's the whole idea of you're going to do multiple derivatives, and you got to figure out which one do I need to use right now, right? To make the sign diagram, I use f prime because I want to know the slopes. To get the points, I use the function itself because that's what it does. That's its job, is to tell me where the hell the function is. Where are we at? Did somebody do that? What is negative e to the negative 1/2 divided by 2? Square root of that. 1.9, I don't know. 2, I'd say like negative 0.2. I don't know. Total guess.
And negative 0.406.
Yeah, always half. So what? So you get negative 0.40 something?
406.
406? Maybe. Everybody else got to. Everybody else is like, she did it. I'm not going to do it. All right, and then the max will be at 1/2 because it goes up and down. So it'll be at 1/2 comma, and this would be positive e to the negative 1/2. Divided by 2. So this is going to be a positive part of that thing. I like it. I like it a lot. Okay. And if this question is on a place where I let you use a graphing calculator, if I was you, I'd be smart and graph the damn thing and just double check what I'm getting, right? Not a bad idea. When we get to the point where we're going to do a lot of analysis and then graph it based on what we get from our analysis. I'd much rather see a wrong graph based on what you did. If you made a mistake here, I want to see that on the graph. Instead of a perfect graph and mistakes in your work. Because that means the graph came from the freaking calculator, and that's bullshit. I want you to see, I need to see you interpret the computational stuff and what does it look like visually. I need to see that connection. I don't want you to just put the right graph down from the calculator. You'll never notice. No. Okay, does that make sense? People hear that and say, I want you to make mistakes. No, I don't want. I want you to work with mistakes you make and show me what that translates into. You'll get more points that way, believe it or not. Okay, one last thing, and then I'll let you guys out of here. To be honest, I've sort of skipped 4.2 for a moment. I was trying to figure out if I want to do that today or wait. 4.2 is sort of it kind of makes sense to put it where they did. It's a thing that's used in a lot of theorems coming up. Same time, it's kind of like out of place in a way. Yeah, plenty of time. Let's do this. I want to talk about the second derivative, and then tomorrow we'll come back and do 4.2 and finish up 4.3. Don't forget the quiz. It's Thursday. What would the second derivative tell you? How do you get to the second derivative? Well, you have a function. You take a first derivative. And what does the first derivative tell you about that function? Slope. Now be a little more general. It tells you how the function's changing as you change x, right? How the function is changing as you move along in the x-axis. What's the function doing? Is it going up or down? That's the increasing, decreasing intervals, right? This is a function in its own right. Do you understand what I mean by that? It happens to be the derivative of some other function, but any function you make could possibly be the derivative of some other function. It doesn't, I don't know if you know what I mean by that. It's a function. If I take its derivative, I interpret it the same way I always would. So what would its derivative? The derivative of the first derivative tells you how the slope is changing as you move. Because what's f prime? The slope, like you guys said. So what's the derivative of f prime? It tells you how the slope is changing as you move along. So if you ever heard in the news, the economy is, like, what did I say? The national debt is still going up, but not as quickly. All right, well, that's a second derivative. That means the slope is still positive, but it's getting less positive, and we're hoping it's going to do this thing, right? More than likely, it's going to do this thing. Oh well. You guys kind of with me? We hear second derivatives all the time in the news or whatever. You just don't even realize that's what it is. So let's see. So if I had a function like, let's just do a nice normal little function we kind of go back to all the time, little cubic. So obviously here, what's f prime? Is it positive or negative? Positive. Now watch. As I move along this, as I move, what's happening to my slope? Is it getting bigger or smaller? It's the slope. So look, isn't the slope here like stupid big? And now my slope is getting smaller until it becomes negative. So through this whole region, the slope is getting smaller. So the second derivative would be negative. That tells you how quickly that's changing. Since the slope is getting smaller across here, that must be negative. And do you see how visually that translates into cup down? It's kind of nice. The negative slope tells me the shape is cupped down. You guys all, you see that? It's almost too nice to believe. So if f double prime is less than 0, then it's cup down. It won't hold water. It's another way. Okay? Now somewhere in here is that, somewhere right here is that most negative slope idea that I was talking about before. And once you're past that most, let's say it's right there. Once you're past that, what's the slope doing now? Less and less negative until it's positive now. So in this whole region, the second derivative should be positive because now my slope is getting bigger, right? My slope was negative, now it's getting bigger, meaning in that direction on the number line. Smaller meaning in that direction on the line. Don't say it's getting bigger, negative, or something. No, that means it's getting smaller. You guys with me? So over here, it is greater than 0. So that means it's cupped up. More formally, this is called concave up, and this is called concave down. Did you know that concave, convex? Concave is the one that makes a cave. So we just look at these both as concave. Here the cave is up, here the cave is down. So that's concave up, concave down. But I like cup up, cup down. Up is positive, that kicks ass. Thank God for that shit, right? Makes sense. If it's positive, it's up. If it's negative, it's down. So let me ask you, if you knew a critical point, there was a critical point somewhere, and it was concave down through that critical point, is that a max or a min?
Max.
Max. If it's concave down through a critical point, that's going to be a max. So that would be the second derivative test. It's almost too nice to believe. Don't worry, I'm going to formalize it, right? So, for example, let's do a function that's not too freaky. I got this function. Let's do a cubic. Well, let's just make one that that's, let's see, x cubed minus 3x squared. Yeah, I like that. That's fine. We'll make it nice and simple. So if I do f prime, I'll get 3x squared minus 6x. And if I do f double prime, I get 6x minus the other one. 6x minus 6. What are the... Is everybody cool with that? What are the critical points for the first derivative? Yeah, if you factor this, you get 3x, x minus 2, right? So you get x equals 0 and x equals 2. All right, let me stop there. Is that cool? Factor it so I can see what makes it 0. What are the critical points for the second derivative? If you factor this, you get x minus 1. Didn't really need to factor though. We're going to get x equals 1. So we do still call them critical numbers or critical points for the second derivative. That's where the concavity might change. Now, if this is less than 0 and this is more than 0, then that most negative in this case has to be where it... If this is less than 0 and this side is more than 0, this most negative point must be where it's 0, right? So that's what the critical point of a second derivative means, is that's the place where the cup down joins with cup up. It's that one point that's neither cup up or cup down. Because it's 0, it's not up or down. It's the joint, it's where they connect. We call this point an inflection point. Think of an old movie with Keanu Reeves. It's an inflection point. It's not quite the name of it. Now, just like with first derivatives, where the second derivative is 0 is not necessarily an inflection point. It could just be a little trickster dude. It could be like, I'm going to change, no I'm not. Right? Just the same way with the first derivative. So I can check it out. So if I do, now let me show you the second derivative test. If I evaluate the second derivative at the first derivative's critical points. You guys were cool with this a minute ago. If I put a 0 into the second derivative, what's it come out to be? Negative. Which means through 0 it is cup up or down? Down, which means that critical point must be the location of a max. You guys? You see what I mean? That's just so flippin' easy. If the second derivative is something I want to take the time to do, right? And the second derivative is freaking easy as shit, right? So hell yeah, I'm going to do the second derivative test. It's so easy. If that second derivative comes out negative there, that must mean it's cupped down. So there's a max. There's a max at 0 what? Zero, zero. You plug a 0 in the function, you get a 0 out. 11. What about f double prime at the other critical point, at 2? When you plug a 2 in here, you get, don't care about the number, it's positive. Is that cool? 12 minus 6. That means it's cupped up, which means there must be a what at 2? A min at 2. Is a min at 2 comma what? Where are you plugging in the 2? I'll tell you what to put the 2, Jeff. Put the 2 in the function. I want to know what the point is, right? Where this thing is. Not what it's doing there, but where it is. So 8 minus 12. I'm going to put a 2 in to see where the point is, right? That's what the function does. So here all the points are. That's much quicker than that sign diagram thing. Yes?
So you said the best time to use that obviously is when the second derivative is easy.
Yes!
But if you ask us for the inflection point, we should do it regardless because that's the...
No, yeah. I mean, here right now I'm just saying if all I care about is where the max and min is, and I don't say anything about concavity, you wouldn't normally have to do a second derivative, but since it's so easy, you do just so you don't have to do the sign diagram stuff. Now, if I ask you where the inflection point is and where's concave up and down, then you have to get the second derivative and look at it the same way we did the first derivative. So, concave up and down. It's the last thing we're doing, by the way. I see my guy's getting very antsy. That's all right. Concave up and down is very much like increasing, decreasing. Right? I make a sign diagram again. I investigate the second derivative this time. I see where's it negative, where's it positive. We already kind of know here. So the critical point is 1. This is where it's 0. So below 1, it's negative. I already put 0. You guys see what I'm saying? I already checked 0 out. It came out negative. And above 1, it's positive. Is that cool? I put a 0 in. I put a 2 in. I already know that. So that means that on this interval, it's what? Cup down. And on the interval 1 to infinity, it's cup up. So is 1 an actual inflection point? Is 1 the location of an inflection point? Yes, it does change concavity. So there's an inflection point at 1 what? Where are you going to put 1? In the original function to figure out where the point is. So 1 minus 3 is negative 2. So 1, negative 2. There is an inflection point. That joint between the two. So if we graph this thing, let's see if it matches with our expectations here. So see here, it should be, well here, without the first derivative test, oh well, we lost some information, but too bad. I know it should be cup down here, cup up there. Let me see if you guys can just bear with me for a second. If I do this, right, I'm just going to recover what we said here. If I figure this out, that means like if I use 1, I put a 1 in there, I get 3 minus 6, it's negative. They each have a multiplicity of odd multiplicity, so it's going to change signs. So I know it's going to look like this. It's going to go up. Isn't there a max at 0? Like matches to this. It's going to go up, and it's going to hit 0, it's going to turn around, it's going to go down, it's going to hit this one, and it's going to go, it should look like that. And is that concave down like I said? Yeah. And that's concave up like I said, right? Sweet. So of course if you graph this, I'll let you do that on your own. And it's how it's going to come out. We knew it's going to be cubish. It's going to look like this. Yes?
So instead of using the sign chart, we just do the second derivative.
Yes, if all you're interested in is the location of the local max and min, then the second derivative test does that for you. Do you see how I had to go back and do the sign diagram to get a rough sketch based on the slope? You kind of lose that from this, right? You don't see that here. That's the downside. But if all you care about is the max and min locations, second derivative test is great if the second derivative is easy to get and nice to work with, right? That's not always true. You know this. Okay, so we still need to go back and do 4.2. And there's definitely a few things to finish in 4.3. The really funny thing about this book is 4.3 and 4.5 are like the same thing. 4.5 just brings in more pre-calc stuff to do at the same time, like asymptotes and all that kind of stuff, right? 4.4 is where we finally learn that thing, L'Hopital's rule. We'll finally be able to use that. It makes limits relatively easy to work with compared to before. So with some of you guys were trying to use it too early. So I don't know if the tutor showed it to you or not, or you just knew it. Okay. I think, yeah, it's not bad. You can stop there. All right. So Thursday we'll have that quiz.
Someone said it's not including 3.8, right?
Yeah, 3.8's not in our curriculum. It's not on the homework sheet. 3.8's not in there.
I just got it today, and whenever I grab something, it's gone.
Okay, so watch this. Go to, and you've got some weird thing. Let's see, where are you at? It's trying. What? Wait, there. You got weirdness. Delete. Now it won't do that.
Okay.
You just had something they didn't understand down there. I don't know who put an arrow in there. It's weird. Sure.
So, for corrections, I started my corrections. I was wondering, for the points back, you said we can get a quarter of the points back. If
You
it's
can
below.
get 11.
Okay, 11. Wait, it's from this one?
Yeah,
Okay.
that's the curved grade. So that's the real grade.
Yeah.
Yeah.
Okay, and then, is the final also curved just like that? Like,
Depends. If I sense that it needs to be, then I'll curve it.
yeah.
Yeah.
One last question. I was wondering what it was saying scheme resulting in highest grade.
Yeah. The grading scheme up here.
Yeah.
See how it's floating?
Oh, you're
So
saying
what I
like-
do is
yeah,
at the
okay,
end,
yeah,
if your final exam is
Yeah,
the
yeah.
lowest, then I'll just count that for the lower
the 20.
percentage.
Yeah, okay, got
So
it. Thank
yeah,
you.
cool.
I'm still having a